Okay, let me try this one more time. Sorry about screwing it up, everybody. So Doppler effect. Let me go right to the first picture here. If you were like an ambulance coming towards you, okay, the ambulance on its own would be giving off sound waves. Okay, but since the ambulance itself is moving, the ambulance would actually be like moving into those sound waves, and it would actually compress the sound waves that are moving towards you. If the sound waves are compressed in, what does that do to their period? Shortens their period, which also kind of shortens their wavelength. Does that make sense? Well, if you shorten a wavelength, what does that do to a frequency? Makes it higher. And so it should be higher. You should have a higher frequency right here. This should be a higher pitch in terms of like a note. So these are going to be shortened wavelengths, which means a higher pitch. Like the frequency will be higher. Does that make sense? The opposite happens as the ambulance leaves you. So now the ambulance is going away from you. And what ends up happening is the waves that come out of it are actually further apart. You see how these ones right here are now further apart than they were beforehand? And so those waves that are traveling backwards towards you, the actual ambulance is like carrying it with them a little bit. And so they get elongated. So over here, you're going to have a longer wavelength, which means a lower pitch. And so the note you hear over there is a lower note. Does that make sense at all? So it has to do with like a compression of waves based on the actual object in motion, causing those waves to not be going out like in perfectly concentric circles. If I use the word concentric, do you guys know what that means? Okay, concentric circles would look like this. Here's a circle, here's another circle, here's another circle. Those circles should never touch each other, kind of thing. Like they're perfectly spaced from each other. This circle right here is not concentric with the other circles. Like it doesn't have the same like middle, if that makes sense? The same origin. Let me play that video one more time just to make sure that it's clear how the pitch works then. Select, that's what I want to do. So fire engine is coming towards you. As fire engine is coming towards you, the waves are getting compressed ever so slightly because of the fact that the engine is moving. Then as it pulls away from you, the sound waves are actually having to come back towards you. Does that make sense? Like the engine is going the other way, so sound waves actually have to come back to you, but since the engine is moving that way, it actually stretches them ever so slightly. Does that make sense? Yeah. So I've got a lot of pictures, and then we'll do 3 examples. So here's an animation of like a car emitting sound, and as the car moves forwards, you see how like the waves in front of it are getting just squished a little bit, whereas the waves behind it are slightly longer. Okay. In terms of other pictures here, it's all about wavelength. As the ambulance is going towards you, the wavelength is actually going to get shorter. As the ambulance moves away from you, the wavelength will actually get longer. What else do I got for pictures? Here's a picture of a police car I found. Same sort of concept here. As the police car is moving this direction, these wavelengths are squished. These wavelengths are pulled outwards. Does that make sense? Lots of pictures, basically. Okay, I'd like you guys to know another term. We actually have like a physics term for this. It's either known as blue shift or red shift. Those are like some physics terminology you might hear, especially if you're talking about people who are astronomers. This phenomena also happens with light, not just with sound. But usually the light has to be happening with like galaxies that are moving very fast and also emitting light. We can actually observe very, very faint differences in colors of light. Okay, here's the basic idea. Red, just so you guys know, red is basically about 780 nanometers, whereas blue is about 390 nanometers. Which one of these has a higher wavelength? Red or blue? Yeah, red has a higher wavelength, whereas blue has a lower wavelength. Okay. So we just use the term red shift and blue shift to describe blue is when you make wavelengths lower. So you see how all of these blue colored waves right here all have a lower wavelength on the side over here? They're flipped, by the way. I couldn't get a diagram that had blue on the same side. Does that make sense? So like here, this blue wavelength is on this side here. Whereas over here, all of these wavelengths are slightly bigger. These have higher wavelengths. And so we call that a red shift. Does that make sense at all?
Lower, does that mean like shorter?
Yeah, like lower wavelengths are shorter, and the shorter the wavelength should mean the higher the frequency, which means that like in terms of like musical notes, it's going to be a higher musical note. Whereas a red shift means you're actually pulling away, which means it's a lower musical note. Okay. So I just need you to know these terms. Blue shift means lower frequencies. Red shift means higher frequencies. So as sorry, I'm using the wrong term here. Blue shift means higher wavelength. Oh my goodness, I'm totally screwing this up. Blue shift means lower wavelengths. Okay, so a blue shift with a lower wavelength is when the ambulance is coming towards you. Okay, maybe I'll write that down. Things coming towards you are blue shift. Things going away from you are red shift. I need to flip this diagram here. That's the reason why I'm getting confused, because I have red on this side of this diagram and I have blue on this side over here. Does that concept make sense? I'll try to do that over the next couple of examples then. Okay, here's a formula. This is the last formula we need to pick off of your data sheet for the unit. The formula is F equals V over V plus Vs times Fs. Okay, so we got to keep some things straight here. Okay. F is the apparent frequency. Okay. That apparent frequency is the frequency that you're going to hear. Okay, which will either be higher or lower depending on how things work. The F with an S next to it, I don't know why there's not an S next to it here. That's this guy right here, is the true frequency. So that would be the frequency that would be emitted if the thing wasn't in motion. Does that make sense? So like if the ambulance is just sitting there giving off a siren, that would be this number right here. Okay. V is going to be the speed of sound. And to keep things simple, unless I say otherwise, we're going to go with speed of sound as 330 meters per second. If I give you a different number, though, use that different number. And then the last number you need is the velocity of the source, which really means we need to know how fast the ambulance is traveling. Does that make sense? Let's try an example. It's actually not that hard. So you've got an ambulance. The ambulance is giving off a frequency of 8,000 hertz. So if the ambulance is just sitting there, you're going to hear 8,000 hertz. But if the ambulance is moving closer to you, what would happen to that frequency? Would it go up or down if it moves closer to you? The frequency would go up. Yeah. Yeah, you're going to get a higher pitch. If the ambulance goes away from you, the frequency would go down. Does that make sense? In terms of shifts then, in terms of the red and blue shifts, as it's moving towards you, that's the blue shift. As it's moving away from you, that's called the red shift. So my question here then is, what is the pitch difference that you're going to hear? So I'm going to have to do this twice. And that's where the plus or minus sign comes here. Because sometimes we're going to have to add the speed of the source, and sometimes we're going to have to subtract the speed of the source. Does that make sense? That's why we're going to do it twice. So let's try this formula. The frequency you'll hear will be based on the velocity of sound over the velocity of sound again, plus the velocity of the source, all times by the frequency of the source. So v, velocity of sound. 330, yeah, we'll go with that. Okay. We actually reuse that 330 right here, but then I have to add the speed of the ambulance, which was 28. And then all of this gets times by the frequency that you actually would have heard, which was 8,000. Alright, so 330 divided by 330 plus 28. Take all of that and times it by 8,000. I now have a frequency of 7374 hertz. Is this when the ambulance is coming closer, or is this when the ambulance is getting further away?
Closer. It's higher, right?
Is this a higher frequency or a lower frequency? This is a lower frequency, which means that the tone is getting lower. And if you remember that ambulance video, when the tone gets lower, it's when it's leaving. So this we just found is the frequency when the ambulance was leaving you, because the frequency went down.
It went down from 8,000?
From 8,000 down to 7,000 or so. So what you were supposed to hear was a note that was up here, but then the note went down to here. That's the right? Like I'm going down with the pitch. Does that make sense? Okay. In terms of red and blue shifts, when you are going away from a source, that is red shift. So this was red. How do I find the blue shift then? Yeah, redo the exact same formula, but rather than doing the plus sign right here, do the minus sign. So to do blue shift, 330 over 330 again. This time we're going to subtract the 28 and still times by the 8,000. As the sound waves are coming towards you, they should have like less distance to travel because you're actually going to be picking up speed. I don't know if that makes sense at all. Now your frequency will be 8741 hertz. Does that make sense? So as the ambulance was coming towards you, the frequency was going to be higher. Then as the ambulance leaves you, the frequency drops. That was that whole down. Make all sorts of weird sound effects today.
So when you want to find blue shift, you subtract them.
Does that make sense? So to find red shift, when they're leaving you, you need to add. To find blue shift, when they're coming towards you, you subtract. Then to answer my question was, well, what was the difference in pitch? So subtract them. 8741 minus 7374 is 1367. And now I should finally throw some sig digs in there. So 2 sig digs based on that 28 meters per second. So let's go with 1.4 times 10 to the 3 hertz. Or you could say 1.4 kilo hertz if you wanted to, because a kilo is times 10 to the 3, I believe. Does that make sense? The formula is kind of complicated looking. Like when you look at it the first time, it's intimidating because like you've got V and frequency, and like there's a VS and an FS, and so it's intimidating. But so long as you can keep track of what numbers go where, really all you're looking for is one frequency goes up and one goes down, depending on whether it's coming or going.
Wait, why is it oh, because it's not times 10.
Yeah, so if I don't put the times 10 to the 3, then I can make it a kilohertz instead. Is that good? Okay, let me do 2 more challenging examples then. Okay. Lisa, could you grab the door, please? Music and like sounds based on musical instruments are often great sources of questions for this. So I did a little research on this. The note A, if any of you guys are in like music class, the note A, one of them at least, has a frequency of 880 hertz. Okay. You guys know what it means when a singer is like flat? It means they're singing like a little too low for what they should be singing. And so in this scenario here, suppose a singer was supposed to be hitting an A, but they're not a really good singer, they're on American Idol, and they're way out of key. Okay? And the note that they're actually hitting is an A flat, which maybe if you're in music you might know what that means, but in case you don't, the frequency is only 830.6 hertz. So you're a little short, if that makes sense. Okay? What would you have to do using a Doppler effect to actually raise that frequency back up, if that makes sense? So if a singer was flat, if they were to, like, for example, run really, really, really fast, could they then raise their frequency up to the note it was supposed to be? Would you need to move towards somebody or away from somebody to make the frequency go up? Okay, so there's the first thing. Which direction would you need to move? If you moved towards, like if you moved towards the source, what would happen is your frequencies would start to get higher as you get closer. So like as a singer, if you were to like be running while you sang, you could make the sound of your voice go slightly higher perhaps. You'd have to run pretty fast though. And that's my question. How fast would you have to be running to then not be flat anymore? Yeah, that's it. We're looking for VS. So we're using our formula again, which is... Say that one more time. Okay, well, let me write out your formula again. V equals V over V plus VS. And then FS. That's our formula. Do we need this to be a plus or a minus sign right here, actually? Well, no, because all we want to do is raise the frequency, not lower it. Good, it is a subtract. Yeah, if you want to raise the frequency, you need to subtract. Because look back at our last example. When we added these numbers last time, it made the frequency go down. That makes sense? So like, if you put an add sign here, frequency actually goes down. So if you put a subtract sign here, frequency will go up. Okay. This frequency right here, which of the two numbers am I looking for this to be? The 880 or the 830?
I don't know which. 880.
This one will be the 880. This is the frequency that we want it to eventually be. So this frequency will be the 880. This frequency at the source, the singer herself or himself is singing flat at the 830.6 over here. So this is what they're doing. This is what we want it to be. The question is, how fast do they have to run while singing to make themselves not be flat anymore? Totally a ridiculous scenario, by the way. The one I'm going to do after it, though, is maybe a little more plausible. Your velocity then will be 330 over 330 minus Vs. We need some algebra skills. How in the world do you get Vs by itself? Okay, so let's start with that. Let's divide out the 830.6. So let's do that first. 880 divided by 830.6 means that it's 1.059, and that equals 330 over 330 minus Vs. Unfortunately, you can't. That's not how fractions in that particular type work.
If you like kind of switch them to like, I don't remember what it's called, but bring the 330 times 3 up and then like put the 1.5 whatever down.
That's a
and
great
then
idea.
subtract out the 330.
That's a great idea. Okay, so what Heather's suggesting here is basically we're going to flip these two sides of the fraction around. This is basically like how a reciprocal works. If I were to give you frequency equals 1 over period, you can just flip these two numbers around anytime you want. That's basically what we're doing here. So, where's the eraser? Here it is. Of course, I picked the little bitty eraser. So let's go with 330 minus the velocity of the source. And then that'll equal to 330 divided by that 1.059 number.
Why do you do that?
Because you're flipping this bottom of the fraction up top up here, and you're taking this guy right here and bringing it down to the bottom again.
What do you add up to?
Give me a second on that one though. So let's take that 330 and divide by that 1.05 number. So that means that 330 minus Vs is going to have to equal 311.475. Do you add out this 330? You subtract it out, yeah. So you have to subtract out the 330. Which means you're going to have a negative velocity of the source. But this number over here is also going to be negative though too, right? Because when you subtract 330, you're going to get negative 18.525. Yeah, so basically you would have to move 18 sigdigs. I actually get all 4 sigdigs. So 18.53 meters per second forward. If you were moving 18.53 meters per second forward while singing, you would no longer sound flat anymore. Yeah, or just not sing flat.
Don't we only get 3 signigs with the 330?
Oh, good point. Thank you. I forgot about that. The 330 only gave us 3. Good catch. Good catch.
Yeah.
18.5 meters per second. Okay, so you might be thinking to yourself, why would we do this? That's such a ridiculous example. Okay, well, I was actually thinking of an example that maybe could have happened over the weekend. Oh, I changed my example here. Okay, I'm going to skip down to C first here. Okay. Imagine that there was a band at a parade, and the band was on a vehicle, and the vehicle was moving. Would the band sound out of pitch? Yes. That's something you might not think of, but like if there was, say, a band on a float or a marching band, right? If the band was moving fast enough on their vehicle slash flatbed truck slash float slash whatever, does that make sense? As the band was coming towards you and as they were leaving you, they would be slightly out of pitch. Does that make sense? So that's actually part of what I want to calculate in this question here. But I'm going to come to that one later. First, I want to do a quick question about what we talked about last day, which was basically about how open and closed columns make certain frequencies. So a bit of a review from last day. Do you guys remember what an open column instrument was? An open column instrument needs to have a wavelength inside of it like this picture right here, where it goes from antinode to antinode, and it creates that standing wave inside. A closed column instrument would be a little different. A closed column instrument would look something like this, and it would have to go from antinode to node. Do you guys recall this at all from last day? Okay. I wanted to do another example on it because I didn't feel like maybe I had covered it well enough. What sort of wavelengths fit inside open column instruments? How much of a wavelength do you need inside of here? At least half. Half of a wavelength would work. Let me see that I can diagram this. Right here, from here up till here, I should use another color. From here up until here is half of a wavelength, because if it could come back down again, that would be the full wavelength. Open column instruments operate on half wavelengths. But here would be actually a full wavelength. Here would be 2 wavelengths. Here would be one. Wait, no, this one's 2 wavelengths. This one is 1.5 wavelengths.
Wait, which one's 2?
This one would be a half a wavelength. This one would be a full wavelength. This would be 1.5 wavelengths. That would be 2 wavelengths. This one should be 1, 2.5 wavelengths. Makes sense? Come on in. Morning, guys.
Carrots are good oranges?
I don't know. Yeah. I don't know.
Oh, cute. Carolyn, I like your shirt sweater thing. I never know what to call those, but I call them something. It's like a sweater.
Shutter.
That doesn't sound good.
Shutter.
That's like, you have that word?
No problem. There might not be any lines. Slowly die. What a head. What a head. Thank you. Everybody get.
Thanks, guys.
Yeah. Welcome.
And that closed one that you wrote down, I wrote that after.
Closed tubes are based on quarter wavelengths, and open tubes are based on half wavelengths. Okay, let me go through this last example and then I'm done for the day. My first question for you is, if a flute is 0.6 meters long, so like if this is the length of the flute, right here, 0.6 meters from one side to the other, and it is considered to be an open column instrument, okay, what is the largest wavelength you could throw inside of there? Well, let me draw one. If I drew all the way up to here and back down, and all the way down to here and back up, that is going to be the longest wavelength I can fit inside of there. Oh, you're right. I'm actually doing this one right here, aren't I? I can do less than that. Let me redraw that. Because I could even go less than that. Well, maybe I should make sure I'm clear here. Of these 5 diagrams right here, which one has the longest wavelength? The top one. Yeah, the top one has the longest wavelength. Here, you have a lot of frequency. This is going to produce a higher note. This is going to produce a lower note. Does that make sense? Based on this being the longest wavelength. So let me redraw that. I could, in theory, fit a wave in here that looks like this, which would be half of a wavelength. So if 0.6 meters is half of a wavelength, what would the full wavelength be? Perfect, 1.2. If a 0.6 meter long instrument can fit just half of a wavelength inside, then how long is that wavelength, the total wavelength? I'd say 1.2. If half of a wavelength is going to be 0.6 meters, then a wavelength on its own will be 1.2, just times by 2.
How did you know how the wavelength?
Basically, you just need to know that an open-sourced instrument is based on a half wavelength, and a closed-sourced instrument is based on a quarter wavelength. So you're either timesing by 2, or you're timesing by 4.
So when it's open, you time.
And if this was a closed instrument, you'd be timesing by 4. So that means that the wavelength of the largest wave you could fit inside here would be 1.2 meters. Okay. My question then is, well, what would that pitch be?
Well, you just use velocity equals frequency times lambda.
That'll work. Velocity equals frequency times lambda. What kind of wave is this? Sound, yeah. So what do we use for velocity? Good. We don't know what the frequency is, but I've just figured out what the wavelength would be. Does the entire wave actually fit inside the flute? Well, no. Only half of it does. But the wavelength would have been 1.2 meters. You have to use the whole thing, yeah. So then your frequency would be, they got an answer? 275? Hertz. Or with sig digs, because I think I only gave you 2. I should have given one more sig dig. It would be 2.8 times 10 to the 2 hertz. That is not a very high note. That is the lowest note the flute is capable of playing. If we were to put more wavelengths inside the flute, like for example, this would be the lowest note right here. Up here, that is going to be a higher note. Why will this be a higher note? Well, because there's more wavelengths inside there, meaning that the wavelength itself is shorter. If the wavelength itself is shorter, the frequency would then need to go up. That make sense? And that's the basis on how instruments work. Okay. Let me talk about D here real quick. I'll do that one out of sequence here. Let's say the keys on the flute were pressed to shorten the length of the column. So rather than the column being this long, the column is now this long. What does that do? Well, it takes a wavelength and it makes the wavelength shorter. The shorter the wavelength, the higher the frequency, and that's basically what instruments do. Whenever you press a key on an instrument, it is shortening the column, thereby making the note go higher. Okay. Anybody play guitar? Okay. Same kind of principle there. If you are playing with frets, if you then put your fingers on those little frets and move them up, it shortens the length of the string, and the shorter the string length, the higher the note.
Like something from Santana.
Okay, let me do this last question here. C, this is the last one I want to do. The scenario I've got here is, let's say this flute player is part of a band, and they're on the back of a flatbed truck going 10 kilometers an hour. How off would the frequency sound? So they're going to sound slightly out of pitch due to the Doppler effect. Let's figure out how slightly out of pitch they'd be. So. Yeah, we're going to have to convert that to meters per second. Why don't we start with that? 10 kilometers an hour. Sorry, this is becoming a mess.
It's 2.7 meters.
Sure. So 10 kilometers an hour is 2.7 repeating meters per second?
Yeah.
Okay. So let's use that formula somewhere way down here. The frequency you will hear will be equal to the speed of sound over the speed of sound plus or minus. Did I say towards or away? As the truck is departing. So if the truck is going away from you, will the note be high or low? And to make it lower, we need this to be the plus sign. And then we need the frequency of the actual source. So your velocity is 330 meters per second. This velocity is still 330 meters per second, but we need to add on an extra 2.77 because that's how fast your flatbed truck is going. I thought that was pretty reasonable, 10 kilometers an hour. That's pretty slow.
Yeah, so people do down Main Street. I'm like, get out of the way.
Or if it's a parade, maybe 10 kilometers an hour is pretty reasonable. And let's say the flute player is trying to play that low note, which used to have that frequency of 275 hertz. How far off will it be then? So 330 divided by 332.7 times by 275. So 273, let's call it, with 3 sig digs. Actually, I was only supposed to get 2 sig digs, wasn't I? So this would be 2.7 times 10 to the 2 hertz.
But don't we subtract that from the original?
Good point. Because I did ask for the difference, did I? Didn't I?
Yeah.
Yeah. So I'll leave that to you guys. If we were going 275 hertz, but then it was 273 hertz, you're off by basically, what is it? 275 minus your answer. You're off by 2.3 hertz. Is it a lot? Yeah, might be a little bit. Might be just enough to make it sound slightly out of whack. We're done. Well, D I kind of talked about earlier. Let me go back to D real quick then. I want you guys to understand how instruments work. If an instrument is this long, okay, it produces a note. If you were then to find a way to shorten the instrument by pressing some keys, which change the way the tubing works, and you shorten the instrument, the note gets higher. Trombone is a good example. When you pull the slide out of the trombone, though, the note gets, you play a trombone, right? Notes get lower, right? So that means you're making the wavelengths available longer, which lowers the frequency, or it makes the wavelengths shorter, which ups the frequency. Okay. All I need you guys to know is that an open instrument, you need to take the wavelength and times it by 2. Whereas if it's a closed instrument, you actually have to times by 4. That's all I need you to know. Okay, questions? Comments, concerns, conundrums, complaints, criticisms?
What do you think tomorrow?
Tomorrow, Friday, rest of today, they're all work days. Quiz on Monday, unit test on Wednesday. So I need you guys to finish your last lab, finish your assignment, and get ready to write some unit tests. So go take a 5-minute break if you want.